So today I will briefly introduce you to two tools, GenSSI and AMIGO2. Both of them are devoted to help model identification of biological systems. So the first question I would like to address today is why would we need these tools at all? Biological systems or the result of a biological system or a question about a biological system is the result of a collection of events that happen through time and through the space. And those events may happen in very different scales. So we may have from nanoseconds in nanometers or even lower than that to hundreds, thousands of years in thousands of kilometers, right? So when we want to build a dynamic model, the first critical question is what is the question I want to address? What is the specific result I'm expecting from the model? And the second question is what spatial and temporal scales I would need to define that model. So imagine we want to model a very simple problem. So we have a batch bioreactor. We introduce a medium there, and we inoculate with some bacteria. And what we want to know is what is the maximum amount of cells or the maximum amount of biomass I'll have at the end when those cells will start to decay, because the medium or the substrates available in the medium have depleted. So, of course, what is happening inside that reactor are lots of different events at multiple scales. But when we decide to build a model, we need to simplify the level of resolution we include into the model. We don't want to build a model which is whose simulation is slower than the real system itself. So we need to incorporate simplifications in our model. And for example, we won't care about things that or events that are happening at the level of seconds or at the level of minutes even. And we will focus only on the, let's say, the relevant dynamics for the question we want to address. So we will build a model as simple as this, where we have two state variables, two relevant variables for our system, the dry weight of biomass, for example, and the substrate uptake. And this model explains the change of this biomass over time and the change of substrate over time. And this description relies on a number of terms here in these equations, which depend on the amount of cells and of the substrate themselves. And we have here a number of constants, which we will call throughout the presentation parameters. And these parameters are the ones which are condensing all these phenomena here. And because they are condensing lots of information in one single number, it's typically the case that we cannot measure these values. So we have parameters which are unknown, but which will definitely condition the dynamics of the system. So different parameter values will lead to different growth rates, to different decays, to different uptake rates, and so on and so forth. So imagine a general biological system and try to explain it with a dynamic model. So we would have differential equations. They can be as complicated as you can imagine, but let's simplify it to something like this. So we have x dot, which represents the time derivative of our state variables, a function which can be as complex as you want or as simple as you want. We will have, of course, this function depending on time. Depending on these controls or stimuli, in the particular case of our fed batch, we don't have any controls, but imagine that in our batch, we don't have any controls, but imagine that we transform our system in fed batch and we are able to add, for example, a substrate to the medium. Then this additional substrate we are incorporating, or the temperature we are manipulating, for example, would be controls that would, of course, also influence the system, but those are manipulable, something I can change. And then we have a vector of parameters which collect all the kinetic constants, decay constants, saturation constants, Hill coefficients, and so on and so forth here in this vector. That can be a combination of known parameters, so parameters that, for example, can be measured, and a collection of unknown parameters, which are those condensing lots of information and cannot be estimated, cannot be measured, sorry. And under this general formulation, we may have many different types of models. So this is another illustrative example, which is a little bit more complicated than the batch growth. And this represents, for example, the circadian rhythm of Arabidopsis thaliana. And this is one of the examples you will find in the tools as illustrative examples. And you will also have many other examples there to play around with different types of number of equations, number of parameters, number of observables or stimulation conditions. We will go into that later on. But as you see here, for example, in this system, we have a stimuli condition, which is the light, which will condition, of course, the circadian rhythm. And we have lots of parameters with non-linear formulations in both the state variables and the parameters. So you will have models as complex as these, models which are even more complex with larger scale, larger number of parameters, and everything is compacted in the same mathematical formulation. So given a model which is potentially able to represent my system of interest and which is able to answer the question I would like to ask about, I would like to reply about my system, how can I find these unknown parameters to be able to reproduce the experimental data? And this is precisely the aim of GenSSI and AMIGO2. The idea is both tools together will help you to find those parameter values in principle. So as you see, we will need experimental data. So let me explain how experimental data is conceived in GenSSI and in AMIGO2. And GenSSI will be worrying a little bit about what is the experimental scheme, but not the data itself. And AMIGO will require the data itself. So that will be a difference between both tools. So the experimental scheme regards all the information related about your experiment. So what you measure in your experiment, the control conditions in which you perform the experiment, the spatial domain of interest, if it's relevant for the problem at hand, locations of the sensors, if it's the spatial domain is relevant and sensors are spatially separated, experiment duration, sampling times, and any information related to the experimental noise. For example, if you have replicates and you are able to account for some information about the experimental noise. So what it will be critical at the time of solving or trying to reconcile the model with data is what you have measured. And this mathematically will be represented as a function here, which will depend on the state variables typically. So for example, in our batch culture example, we may be able to measure the dry weight, and we will be able to measure the uptake of sugars. So in that case, we have two observables which exactly correspond to the state variables. But imagine we couldn't make the uptake of substrates. Well, then we would only have one observable which would correspond to the cell, to the biomass dry weight, right? And it may happen that in sophisticated models, for example, the one I showed about the circadian rhythm, we have 8 or 9 or even more ordinary differential equations, as many as you want, but in that particular case, I think it is 8 equations. We have only 2 observables. So this will be particularly important when trying to reconcile models with data. And the experimental data will try to represent it will be a matrix of data which represents exactly the numerical measurements corresponding to the observed quantities for a given experimental scheme for the number of sampling times we have. So the first question we need to address here, and you might wonder, for example, in the circadian rhythm, is it possible from out of 2 observables estimate all those parameters? So GenSSI is the tool for that. GenSSI will try to answer the question, is the problem solvable in the first place? So does it have a unique solution? And for doing so, we only need to know what is, of course, the model equations, what is measured, so the observables, and if you have more than one experiment. So GenSSI is based on an approach we presented in these 2 papers. In this, we presented a preliminary version, and in this paper, we presented a more detailed description of the method, in which we combine what is called the generating series approach with identifiability tableaus to simplify a little bit the analysis. So basically, the analysis depends only on the model structure, and the idea is to try to describe or approximate the observables as series of parameters dependent only on the unknown parameters, and testing whether the solution of this series is unique. So the software automatizes everything. So the mathematics behind it is a little bit elaborated, and I won't enter into this, but we will need to do lots of symbolic manipulations over the ordinary differential equations, including computing Lie derivatives, computing Jacobians of these derivatives with respect to parameters, drawing these identifiability tableaus, trying to solve a system of nonlinear equations, if possible, to eventually tell you whether the parameters, all of them can be uniquely estimated, only a part of them can be uniquely estimated, or whether there are several solutions for one or several given parameters. So the tool was originally implemented in 2011 in its original version, GenSSI. It is implemented in MATLAB, and it's using the symbolic manipulation toolbox in MATLAB. And later, in 2018, we, in collaboration with Jan Hasenauer's team in the University of Bonn, implemented a second or an update of the tool, which is compatible with SVML models and allows for the multi-experiment capability. The tool is available here in this link, which I'm not sure you can see because of this, but I can send you here it is, the link, and you of course rely on the use of the symbolic manipulation toolbox in MATLAB. For the illustrative example, this batch microbial culture, the model is structurally identifiable. So it is very simple to run. You just write the equations, say what the parameters are to be estimated, And of course, it may take some time for larger models, but you will come up with the result saying the model is identifiable, or these parameters are identifiable and these other parameters are not identifiable. So you can play around with the tool if you want, and if you have any question, please let us know. So once we know that we are able to, well, if the GenSSI comes up with the global identifiability, so meaning that all parameters can be estimated, then we can solve the parameter estimation itself. If the model wouldn't be structurally identifiable, the only solution is to try to reformulate your model, either reducing the number of state variables or trying to reduce the complexity of the different formulations or different dependencies within the model. But typically, there is no other way to solve the issue unless you can add observables to the system. So once we have an identifiable model, we can run the parameter estimation problem. And for this, we will use AMIGO. So basically, the idea is to minimize the distance between the model predictions and the experimental data by allowing these unknown parameter values to change. So we have the model unknowns, we have the experimental data already, but we need to have a distance measure. So AMIGO allows for the definition of several distance measures. The standard is the generalized least squares function. Even within the least squares function, we have several possibilities to define this weighting matrix. So we can have the identity, the maximum data, the mean data, and it can even be completely user introduced by the users. So, for example, to eliminate outliers or to weight some specific measures in specific ways. So there are several possibilities within AMIGO. And also we have the possibility of incorporating information about the experimental noise through the log likelihood functions. And here again, we have several possibilities depending on the type of experimental noise you have in your system. So the problem is formulated and solved within AMIGO as a nonlinear optimization problem. So we could think on a very naive way of solving the problem, just running hundreds and hundreds and hundreds of simulations of parameter values and try to see which is the one best accommodating to the data. But in AMIGO, we solve it as an optimization problem using a frequentist-based approach. And the idea is to minimize the cost function, minimize the least squares over the log likelihood function subject to the system dynamics and the observation function within and a box or a hyperbox of parameter values. We can also handle constraints on the states or the parameters, but I haven't included it here in the formulation just to make it a little bit simpler. So the idea is to use an optimizer, which is able to automatically generate parameter solutions and eventually converge to the best possible solution. So AMIGO offers a collection of local and global optimizers for doing so. Local optimizers are well suited for problems with one single optimum, so convex problems. And AMIGO includes several possibilities. Here, probably the most efficient are the ones which are precisely developed to solve least squares problems. And we have 3 alternatives for that. But when the system is, when the model is noisy, for example, or when we have discontinuities for whatever reason, we also have direct search methods which are able to solve the problem without the need of using gradient or Hessian, which would be required for continuous least square solvers. But we also and provide a collection of global optimizers. It is rarely the case that in parameter estimation the problem is convex with one unique solution. We typically face search spaces with several peaks, and finding the global solution requires a global optimizer. And in this case, we also offer several possibilities. So currently, we have a dynamic hill climbing approach. We have differential evolution and enhanced scatter search, plus hybrid combinations of global solvers such as differential evolution with any of the local solvers we have incorporated in the tool. By the way, enhanced scatter search was also developed in the group in a work led by Julio Banga, and I'm sure he presented it when he presented AMIGO. So let's go back to our illustrative example, and in this particular experimental set, we try to estimate the data. And because this is a synthetic example, I know precisely the value of the parameters I used to generate the data. And we generated 11 sampling times for the two state variables, so we can measure both the dry weight and the uptake of substrates, and we tried to estimate the model parameters. So we compare the solutions using the standard least squares with the log likelihood function using the standard deviation of the generated data. As you will see, the values obtained for the different using different cost functions are different because log likelihood will tend to reproduce better those solutions with lower experimental noise. And in both cases, we failed to achieve let's say, the real value of the parameters, even though the quality of it is very good. So a second question that we may come up with is whether it is with the experimental data we have, whether it is possible to estimate the parameters with accuracy, or how uncertain are those parameter estimates. So in AMIGO, we can run the practical identifiability analysis. This means trying to assess whether or the accuracy of those parameter estimates and whether they can be estimated at all. So we can do it a priori, for example, using sensitivity analysis. So we have the possibility of running local and global sensitivity analysis, and we can do it in parallel with parameter estimation using the Fisher information matrix as a means to approximate the confidence intervals for the parameters and explore the correlation between parameters. And if we do so, for our illustrative example, we will see that, for example, the decay parameter is kind of uncertain. So the quality or the uncertainty associated to this parameter is more than 100%. So any value is possible within this range. The confidence is even a little bit lower when using the log likelihood. And this is the type of outputs you would get also with AMIGO. So this is the correlation matrix between parameters, and you would see, for example, that the decay parameter and the yield coefficient are highly correlated here because we have a positive maximum correlation of 1 almost. So this type of information is very useful and it's very quick to obtain. Of course, it will depend on the size of your model, but it is one optimization, and automatically you get the confidence intervals through the Fisher, provided the experimental data is rich enough to get to be able to compute the inverse of the Fisher information matrix, of course. But you can also do it with a bootstrapping, more robust approach using the function AMIGO RIDent. And the idea behind is to run several hundreds typically of realizations of the experimental data using the information on the experimental noise, and then perform an analysis of the parameter results achieved. And what is nice here is that you can see, for example, clearly here that the confidence interval is an elliptic region, at least in the two-dimensional space. And you can think of a hyperellipsoid in the general space of all parameters. So if we run the robust identifiability for our illustrative example, you will see that the values of the confidence intervals are pretty similar to the ones obtained with the Fisher information matrix. So Fisher information might not be as bad approximation as we originally thought, but it will depend on the data, on the model itself, etc., etc. Running this, of course, takes a significant amount of time, because this means solving the parameter estimation hundreds of times usually. Anyways, as I mentioned before, we have a hyperellipsoid, which is not super nice because we have large confidence intervals for some parameters, and then we also had high correlation between some of the parameters. So this means that we will have a very elongated and large hyperellipsoid, and we could try to, through optimal experimental design, make things nicer, so reduce the confidence intervals and also reduce the correlation between parameters. So to do so, AMIGO2 offers the possibility of solving optimal experimental design, the optimal experimental design problem using the model itself. So in statistics, we have the possibility of running experimental designs, typically with multi-level factorial plans, and then optimizing the number of experiments we could use. But in model-based optimal experimental design, we can focus on the particular problem at hand. For example, we want to reduce the correlation between the yield and the decay coefficient. Then we run the model-based optimal experimental design precisely for that objective. The problem is formulated as a dynamic optimization problem, and we need a few elements for that. So we need the model, of course, including the observation functions. We need a preliminary value for the parameters. We need a scalar function which is able to account for the information conveyed by the experimental scheme we are trying to design. We need to define what are the degrees of freedom in our experimental scheme, and we may also need to impose constraints on the experiments. For example, we cannot measure more than 8 sampling times, or the experiment cannot last more than 8 hours because we don't want to be here overnight, right? So constraints that make the design kind of comfortable for the experimentalists. So we formulate the problem as a optimization problem, as I said before, and we can use as a measure of the information provided by the experiment the Fisher information itself, because we know we use it as the inverse of the uncertainty. If we have a very large Fisher information matrix, what we will have is a very small hyperellipsoid, which means a higher confidence on the parameters, and we can account for that volume using the determinant of the Fisher. So this is the so-called the optimality criterion. But we could also try to make it rounder, and for that we could maximize the minimum eigenvalue of the Fisher information. AMIGO incorporates also other functions based on the Fisher information matrix, but these ones are the ones I could start with. So the problem is solved numerically, and in the case of having the possibility of manipulating stimulation conditions, we would use what we call control vector parameterization to simplify, let's say, the problem, to make it numerically tractable. But this is, of course, transparent to the user. So in the illustrative example, Again, we decided to design the second experiment, taking into account the one we have already. So the second experiment is somehow complementary to the one we have, and we allowed to modify the initial conditions for both the amount of cells and the substrate concentration. And we allowed for the experiment to be free, in this case, between 6 and 15 hours, with 11 sampling times. So this is the second experiment we came up with, and as you see, now the parameter estimation with these two experiments together results in values which are definitely much closer to the originals, and also with very reliable or high quality of the parameter estimate, so very limited uncertainty. In this particular case, we could have probably already designed the experiment without model-based experimental design, because if you see here, we had problems estimating the decay parameter, and this is because we only had two data with in decay conditions. But and that makes very hard to estimate the decay parameter with only two data. But again, this is a simple case, and in highly complicated models such as the one I showed before on the circadian rhythm, it is typically very difficult to come up with an intuitive experimental design which is particularly focused on solving a specific problem in the parameter estimation. So both tools are able, again, to help you in the model identification loop at different stages, so solving the structural identifiability analysis question, whether the solutions are unique or not, and then solving the parameter estimation problem itself, addressing the practical identifiability and the uncertainty associated with the parameter estimates, solving the optimal experimental design problem, and again, contributing to model invalidation, I would say, through the incorporation of new experimental data. So once you have a working model, you can think of using the model for optimization purposes. So, for example, imagine you have a model of an illness, and you want to design what is the optimal drug delivery to improve patients' or to reduce the impact of illness. So you would need to use your model to try to devise which is the optimal delivery of that drug. In our case, for example, we could think on, for example, maximizing the amount of cells in our illustrative example, maximizing the amount of cells in minimum time. And we could try to devise the initial conditions and the substrate composition, or whether we need a fed batch system to achieve that the maximum amount of cells at a given time. So the problem is to find the optimal operation and stimulation conditions to maximize or minimize a certain objective function, or even a collection of objective functions if we consider a multi-objective example. So the problem is formulated as a general optimization problem in which the objective now is completely free, so it relates to performance in quality of your final product or whatever. Energy uptake if you are dealing with bioprocesses or whatever you can think of, and you will have to handle the system dynamics, of course, and constraints that may be related with the safe operation of your system, or with biological constraints if you are dealing with a particular biological system or designing a biological system for whatever purpose. So you will have to deal with different different types of constraints. So basically, if we transform a little bit our example, we still have a reactor. In this case, is a fed batch reactor, and what we want to, for example, do in this particular case is to use our well, yeasts in this case to maximize the production of a certain protein. So we have the model. It is already calibrated. We know the parameter values. Here you have the numbers. So we need to solve the optimization problem. How do I input glucose over time to maximize the production of protein at the end of the process? So we solve that. Again, transparent to the user using control vector parameterization approach. I won't enter into the details. And the optimal profile we would get is something like this. So this would be the optimal input of sugars into my fed batch reactor to maximize the amount of protein at the end of the process. And this was achieved using another task within AMIGO, which is related to dynamic optimization. So if you want to download the tool, it's available here, and you will see it's a folder. There is no installation. You just copy into a path. You enter. It is implemented also in MATLAB. So you enter MATLAB, go to your path, run AMIGO startup, and you will have everything installed for the session. So there are many tasks within AMIGO. Some of them I was not describing today because of lack of time, but you will see that you have regularization possibilities as well for parameter estimation, the possibility of solving inverse optimal control problems when you want to estimate parameters, but also time-dependent functions in your model. You will have several functions for simulation, even to generate pseudo-experimental data, ranking of parameters in connection with sensitivity analysis, and so on and so forth. And in the folder examples, you will have plenty of examples for all the tasks available in AMIGO. So I invite you to go there and to start exploring those examples, because those can be used as templates to implement the new problems. Aside of these examples, we typically publish all the scripts for all the models we developed in the group. So you also have the possibility of exploring in the different publications, the different scripts for different models other than those in the examples. So to finish, I would like to summarize a little bit what I said today. So formulating a dynamic model, of course, requires transforming hypotheses and approximations into differential equations and the observation function, which is connected to the experimental scheme. GenSSI comes into place before parameter estimation and answers the question, can the model be uniquely estimated from ideal data? AMIGO tool allows for simulation, sensitivity analysis, parameter estimation, practical identifiability analysis, optimal experimental design, dynamic optimization, and inverse optimal control. Once you have the model working, you can also solve dynamic optimization problems, which can be multi-objective, because there are multi-objective solvers also available in the tool. And AMIGO2 can be used together with your own models, for example, as black box, so that there is the possibility of even incorporating your own parameter estimation function and exploiting all the additional capabilities in AMIGO. We have combined it, for example, with Cobra Toolbox or NumPy to solve dynamic flux balance analysis systems. And you could also use, for example, the dynamic optimization module to implement optimal experimental design for model selection, etc., etc. So if you have any questions, please feel free to contact me. I will be happy to answer. And or if you think we are missing capabilities, we sure do. Just let us know, and we can try to make them available. And of course, I would like to finish with acknowledging my team for their support, of course. the collaborators in the implementation of AMIGO2 and GenSSI, and the funding that keeps the team and the tools running. And thank you for your attention.